The ALU operates by receiving information from the registers, and the control bits indicate what operation to perform on this information. The result of the selected operation is sent back to the registers. Suppose now that we want to implement an ALU that receives 3 control bits and executes 8 operations. I have designed this ALU so that when S2 is 0, we select to execute one of 4 logic operations, and when S2 is 1, we select to execute one of 4 arithmetic operations. As we have demonstrated with the multi-bit adder circuit, it is often easier to design 1-bit modules that we can piece together to create larger multi-bit circuits. In this lecture, we will design a multi-bit ALU by first designing a 1-bit ALU. We can create this 1-bit ALU by designing a logic unit that executes the logic operations and an arithmetic unit that executes the arithmetic operations. The details of the arithmetic unit are covered in a different lecture. We will then need to create a circuit that would select which operations result to send back to the register. This circuit is called the multiplexer. As we mentioned earlier, if we want to choose between logic operations and arithmetic operations, we simply need to look at the value of S2. Rather than derive an expression that is based on the many input variables of the ALU, let's use abstraction and call the output of the logic unit L0 and the output of the arithmetic unit R0. We can then effectively ignore the logic unit and arithmetic unit to simplify the problem. To create our multiplexer, we want to use S2 to select between L0 and R0. When S2 is 0, the output will equal L0. When S2 is 1, the output will equal R0. We can derive a minimal expression from our K-map by selecting the 2 essential prime implicants. This circuit is called a 2-to-1 multiplexer because it receives 2 data inputs and transmits 1 data output. Generally, we draw multiplexers as a trapezoid with the data inputs on the broad side and the data output on the narrow side. We index the data inputs starting at 0, and we place the selection input bits here. We index the inputs so that the binary number encoded by the selection inputs matches the index of the input bits. If we want to select between more data inputs, we simply need to increase the number of selection inputs so that they encode the number of data inputs. For example, for a 4-to-1 multiplexer, we need 2 selection inputs to encode all of the indices of the data inputs. We then use the binary number encoded by the selection inputs to indicate which data input is transmitted by the output. For example, when the selection inputs are set to 2, the output is set to the value of I2. We can use this 4-to-1 multiplexer to create our logic unit. When S2 is 0, we simply need to use S1 and S0 to select which operation to perform. We implement the logic unit by pairing each operation with the data input that matches the binary encoding of the selection inputs. In this lecture, you learned about the multiplexer circuit and how we can use the multiplexer circuit to simply implement complex circuits like an ALU. An N-to-1 multiplexer selects 1 data input to send to the output by encoding the data input's index with a binary number within the selection inputs. Therefore, a multiplexer needs a minimum number of selection inputs based on the number of data inputs.